Okay, good evening everyone. Hopefully I've managed to set everything back up okay. So let's begin. Last time we're doing some refactoring, and that left us with a few crates. It left us with a rules crate, as well as our main library crate and the binary crate. And I think all but like 2 warnings, which are around the row and column stuff, have been resolved. So I'd like to encourage you to say in chat if there's anything that you spot that I'm doing stupidly, or if the music level isn't good. I'm still struggling to get levels exactly right. I think sometimes it gets a little loud, so I'll turn it down a little, and hopefully that won't be too much of a problem. So my goals for today are that what I would like to do is to split out the stuff that we currently have as constraints, because realistically the set of constraints that we have, and let me bring them up, singles and the given digit. Well, given digits are, for want of a better term, rules, or at least the presence of given digits is a rule, even if the digits themselves become a constraint. And the singles are more like techniques than constraints. So part of what we're going to do today is to split this stuff up into rules, constraints, and techniques. But to get there, what I really want to do is I want to get rid of the new Sudoku member of puzzle. So this function should not exist. Instead, what we should have is a Sudoku grid rule that understands how to build this stuff, and probably a region constraint, or at least a non-repeating symbol region constraint, and all of that stuff. So we're going to build a puzzle builder, and we're going to try to separate things out so that, again, we've got a little bit more of a consistent construction of these things. I don't think that's necessarily going to leave us with a particularly cleaner main function, but at least I'll feel a bit better about the APIs and the mechanisms that we are using to construct this stuff. So what I'm going to do is I'm actually going to... we're going to do it as a separate file. Let's just do it in here for now. We're going to have a puzzle builder type. So where was our puzzle type? So our puzzle type is here. And let's put together a puzzle builder. And I'll stick debug on it just because we may end up needing that. And puzzle builder is going to have the same mechanism for dealing with symbols, because we're going to be able to insert symbols into the puzzle builder. We're going to be able to give it constraints. And again, we're going to have cells, regions. In fact, I may as well just copy these. Cells and regions are going to be copied over. I'm not going to copy over implications, and I'm not going to copy over row calls. And my feeling there is that implications come from constraints preparing the board, and row calls comes from us going from puzzle builder to puzzle. And the reason that I think that's valuable is because I think that it allows us to create all of these caches at the same time. So like row calls in theory is a cache from coordinate to cell index, and we could equally well have a cache of cell index to what regions that cell is in, and so on. Like regions are cache is a map from region index to cell number. So all of those things I think we can build as we go. So we're going to be doing puzzle builder, and what we're going to do is we're going to end up mapping puzzle builder to we're going to map some of the methods that we've got at the moment in puzzle into puzzle builder. What I'd like to do is I'd like to have phases for building a puzzle, but I'm not sure that's necessarily needed. Let's think. What I'm thinking here basically is that, do we need to construct all the cells before we construct all the symbols, or all the symbols before we construct all the cells, or anything like that? And I think actually realistically it doesn't matter. The order in which we deal with the rules can deal with that sort of stuff. Let's not worry about that for now. So we are going to have, and we'll stick it here because realistically we do puzzle builder before we do puzzles. So we're going to have, do we need a new, or can we do puzzle builder, can that derive default and thereby get new? Because empty vec, empty vec, empty vec, empty vec is a reasonable implication. Yeah. And then in theory we could have puzzle builder from puzzle definition, which would potentially allow us to construct other things. So we're going to go with that, which means that one of the first things that we're going to need in puzzle builder is the ability to add a symbol set. So we're going to have pub fn, what we're going to call this one, we're going to call it add symbol set, which takes a borrow mute self and a raw symbol set. Oh, this is interesting because it's going to end up with raw symbols, and I'm not sure I want raw to be exposed. So actually we're going to go pub fn new symbol set, which takes a borrow mute self and gives back a symbol set builder. Ha! And that's going to have a plus tick self, or plus tick underscore, or I'll tell you what, we'll work that out when we get to it. And that's going to have a to do, and the symbol set builder is going to come from symbols because it may as well. So let's see. These are our types. There's raw symbol set. So let's go straight after raw symbol set. We can say, and putting documentation on all of this will be lovely, but let's worry about that later. So this is a pub struct symbol set builder, and that actually does need a tick p for puzzle, because we're going to store in here the puzzle, which is a borrow tick p mute puzzle builder, and we're going to also store in here the symbols that we are constructing, the name of the symbol set, and so on, which is effectively just a raw symbol set. So we're going to call this the set, which is going to be a raw symbol set, and that's probably good enough. And what that's implying to me is that we should probably say that the new symbol set takes a name, and we need to write our symbol set builder type. So symbol choice, symbol ID, symbol. Let's pop it in here approximately, so things are approximately in the same order. And we're going to have within the crate new, which takes name and gives back self, but it's not just going to take a name, it's going to take a puzzle builder, borrow mute puzzle builder, and this is essentially going to be self, where we give in puzzle builder, and set is going to be a raw symbol set, where name is name.into, and symbols is just an empty vector. So implicit lifetime that's been elided is not allowed, so that's an import tick p, symbol set builder tick p. Explicit lifetime is required in here, that's got to be tick p. That's missing a comma, and we're getting somewhere. So in here it's going to be symbol set builder new self and name. And the reason that I want to do it this way is that I want the symbol set builder to hold that borrow mute, so you've got to complete the construction before you can do more puzzle builder stuff, and that means that we can then insert the whole raw symbol set into the puzzle builder in one go. And the way that we're going to do that is we're now going to have the ability to insert a symbol. So we're going to have pub fn push, which takes borrow mute self, and at the moment is symbol new public. Symbol has width. What's public in this? I'll tell you what. Let's just very quickly do cargo doc like that. Let's grab a new browser window. Let's stick an open on that. And let's double check. So symbol, which is what's exposed, does have a new, and that is public. So that's good enough for us. I don't quite know why that is not working, but we'll get there. There's probably no depths is cocking that up. But importantly, we can create symbols. So push is going to take a symbol by value. And it's going to be self.set.symbols.push symbol. And then we're going to have new symbol set push. Is that ooh? So what that could do is that could consume self and return self. Could return a borrow mute self. No, realistically, we're okay with this. This is then going to have finish, which is going to take self. And what we're going to do here is we're going to say puzzle builder and set is self. So we're destructuring, and then we can do puzzle builder dot push symbol set. And I'm just thinking that it might be nice if this returned the symbol set index that we're working with. So let's think about that for a moment. Is that reasonable to do? Symbol set index. Yeah, because we might want to use that when we're constructing constraints or something. So let's do pub create fn push symbol set, which takes a borrow mute self. The set, which is a raw symbol set. Oopsie. And returns a symbol set ID. So we're going to go self.symbols.push set, and then we're going to go symbol set ID. Yeah, allowed to of self.symbols.len -1. And then here we are pushing the symbol set. We're going to return a symbol set ID. And so that's hopefully closed the loop on all of that. Andy said, never understood why the convention for lifetime markers are usually single letters. Laziness in my case. I did consider calling it tick puzzle rather than just tick P, but generally speaking, when I only have one lifetime marker, I tend to just use a single letter. And the compiler will tend to use single digits where it can, so that it distinguishes between what the compiler is saying when it says, oh, hey, this lifetime needs to live as long as this lifetime. And humans will tend to use letters. I mean, I don't object to calling it tick puzzle instead. You know, if that makes more sense to others, we can do that. But it's not going to show up very often, so I think I'm probably going to stick with tick P for now. So we've got the ability to construct symbol sets. That's the first thing that we need for our puzzle builder. The second thing that our puzzle builder has are cells. So we need to be able to push new cells into the puzzle. So let's do that. Let's have pub fn new cell. And that's going to take a mute self and a cell, which is going to be a cell info. So is cell info sufficiently public in being constructible? I At the moment, it only has formatting ability, so we're going to have to be able to create cell infos in order to do this, and I'd rather not faff about too much with this stuff. So here's a question. Do we allow you to put the row and the column into the cell? Yes, I think we do. And then I also think that we have to ensure that that is unique. So perhaps we do need the row col hash here so that we can actually ensure that it's unique when we do this. Yep. Ooh, I do like it when my own ideas fail. So we're going to take that cell info and we're going to go if self.row_cols.contains key cell.row cell.col. In fact, I don't think we need to do that. We can just go assert not that attempted to insert duplicate row col. I think that's probably good enough. And then we go self.cells.push cell. In fact, we can go ret is cell index of self.cells.len. Do this before the push this time. Push the cell, row cols, insert row cell col ret, push that and return. And so therefore we're going to need to have a cell index come out. And we're going to need that because as we are constructing everything in the puzzle, the rule that's constructing the puzzle grid, it's going to need to know the indices of all of the cells that it's added so that it can then, for example, create regions using those cells. Remember that row and column in a cell index, a cell info, is entirely sort of informational. That's just so that we can like display, oh, it's this cell which is row 1 column 1 kind of thing. It's not anything to do with Sudoku rows, Sudoku columns, or what have you. Okay, so we can create a new cell which also has the effect of pushing into the row columns. Next step for Puzzle Builder is to be able to add constraints. For now, we're just going to copy that from here. In fact, we're going to copy add region as well, probably, but we may not even have an add region. Initial board, add constraint. Here we go. So we're just going to copy that for now up into here. My goal basically is to get to a point that you can't have a mute. You don't get a mute puzzle, or rather, no method on puzzle is borrow mute. No, because except for the inferences. There we go. Yeah. Okay, and now we need an add region, which takes a borrow mute self and a region, and gives back a region ID. So again, this is about adding regions which are informational. They're groupings of cells. In fact, realistically, we instead of calling them regions, we could call them groups, but we'll call it region for now. And rules that we have here are that region names probably should be unique. So let's do this. Let's assert not self.regions.any or iter any r.name equals region.name. Attempted to insert duplicate for region.name. So we're not allowed to insert a duplicate region. I wanted us to have a way to say, given I've got cell blah, what regions is it in? So I think that means that Puzzle Builder is going to need this as well, which is cell regions. It's a hash map from, was it hash map or is it going to be a vec? I mean, it doesn't need to be a hash map because cell indices are always just usizes. So let's see, cell regions is a vector of region IDs. Yeah. And when we push a cell, we also push an empty vector of region IDs. So that means that that vector will always exist. And then down here, we can go for cell in region.cells. See, that's going to call into iter on region.cells, which is going to screw up because it's going to destructure the region. That gives us borrow cell indices. So let's actually do this explicitly, and let's do that, and let's do that. And in fact, we can say for cell index cell, which is getting us that usize out, and then we could go self.cell regions cell.push ret, which we're going to construct here. So ret is going to be self.regions.len as a region ID. And then we're going to go self.regions.push region, and we're going to go ret. So construction process here, we're making sure we can't insert a duplicate region. Then we're going to create the region ID for it. We're going to push all of those into cell regions, and then we're going to push the region in and return. So what this is getting us is the ability to say, for this cell ID I have, what regions is it in? And that will be useful later when we start to add, rules to do with whether or not things can be in regions, or when we start to look for tuples in one region overlapping another region and how that affects which symbols can be where. Hope that made sense. So we've now got add region, we've got row calls. So the only part of this whole method now, so this is the new Sudoku thing. So it created the symbols, it created the cells, it created the regions for the rows, the columns, and the boxes. And then it created the puzzle. Oof. Then it found the digit symbol IDs, and it created all of the inferences. This bit here, we're going to actually offload to a new constraint, which we're going to call a non-repeat region, which is just going to be a region that cannot repeat digits within it. And then during the inference construction, we will get to say, that basically this operation, but a non-repeat region constraint will know which symbol set it wants to deal with, because at the moment we're just, we only construct a single symbol set, so we're inserting that symbol set in. I think, in theory, we now have enough. So the final bit that we need here is we need to have, we'll call it build, why not? Which produces a puzzle. And we can say let self. So we're going to do that destructure, and we'll just add all the missing fields in, and hopefully that won't be a problem. And then we're going to return a puzzle with all of those, and implications can just be, what are implications? It's a hash map, so hash map new. And the thing that we've not used is cell regions, so we want our puzzle to have those so that we can retrieve information from them later. So let's add that to here. There we go. And now we can make sure that cell regions is there, and We're getting there. And now here, obviously, this can't construct because cell regions doesn't exist. But we're trying to move this Sudoku initialization out. Let's fix it very temporarily for now. Like that, which is, it's not valid, but it'll leave the compilation working so that we can move on and get on with other stuff. And cell regions is never read. What a surprise. Okay. So if we come over to Kaji rules, we've got pubmod constraints. We're going to have pubmod rules. And rules are going to be, so rules are to do with constructing puzzles at all. That's a very bad bit of description, but who cares? And my theory basically about rules is that for now, we're just going to have the one, which is the I'm making a Sudoku grid rule, but later we can add more rules. So I'm going to go mod Sudoku, which I'll make pub as well. And I'm going to create that. And Sudoku grids. So let's see whether or not we can create a Sudoku rule, which we can use to initialize a puzzle, and that rule, you know, can take a grid size and work with it. Right, so pub struct Sudoku grid. Don't know that it's necessarily got anything in it at the moment. Do we want to have an trait rules? Why not? And again, I'm really not worrying too much about this for now, because we're going to end up with all sorts of stuff in the future for this. So we're just going to have fn apply, which takes a borrow mute puzzle builder, and rules. You have to be able to apply rules to puzzle builders. That'll do for now. So in here, we're going to impl rule for Sudoku grid, and that's missing the apply function. And we will qualify that. So we're ready. So how are we going to know what size grid we're going to do? We'll do it like this. So we'll import Sudoku grid pub fn new size. Do that for now. And now we can actually build the grid. And the way that we do this is we're going to put all of the cells in. We're going to insert all of the rows and columns and regions, and that will be enough. Oh, and we'll then add constraints for the non-repeat regions. Oof. I mean, it's a lot of effort, this, but it'll be worth it in the end, I'm sure. So step one is to construct all of the cells. How many cells do we need? We need size squared cells. So apply is going to have to have a borrow self. That's only fair. Method apply has a borrow self declaration in the trait, but not in the. That's just because I haven't pressed save there. Okay. So let cells equal 0 to self.size times self.size. Map. Don't actually care the digit. We want to go build a. Oh no, because we're caring about rows and columns. So let's mute cells. We actually do want to know the row and column numbers when we construct this, because that would be sensible. So let mute rows and let mute cols. So we're actually going to construct those all at once. Can we do that with boxes as well? Is there a sensible way to do that? Or should we just compute the boxes after? For now, let's assume we're going to compute the boxes after. And in fact, a Sudoku grid is just a specialization of a Latin square. So, I mean, it's possible that we'll end up with a Latin square rule, and the Sudoku grid rule will just say, okay, run the Latin square rule and then build my boxes as well. But for now, let's just do this, the way that, in theory, we were doing it before in Puzzle. And in fact, to that end, let's get rid of that, and look at how we do it in Puzzle. So at the moment in Puzzle, we're creating the symbols, and in fact, we should do that as well. So let's do... Oh, should we? Yeah, because we're going to need them to create the other constraint. So digits are a block, and that block says builder.new symbol set digits. And now we want to push into that symbol set symbols for each of the digits. So set.push symbol new format n. We're going to say let mute digits equals a new vector. No, we can do this one better. We can go 1 through self.size map n to that collect vector of whatever, and then we can find out what's wrong. What's wrong is that I need that. And what are we going to find that we've ended up with? Is we're going to find that we've ended up with that set.push doesn't return a symbol ID for the symbol set because it can't. Because it doesn't know what ID it's going to have. And it wouldn't be right to return a symbol ID. So that's no use at all. So let's go stick a for each on there. So we've pushed those in, and then we can go digits equals set dot finish. And that gives us back a symbol set ID. Now we can extract all of the symbols from that symbol set, which is going to require us to go back and add that functionality in. And that method we can steal from Puzzle. So symbol set was an internal one that gave you a raw symbol set. Symbols takes a symbol set ID and gives us back symbol IDs. So having created the symbol set, we get the symbols out of it, and we can do that by replicating that method in Puzzle Builder. Should really be before build because you're never going to call it after build. And then over here we can go let digits is builder.symbols for digits collect as a vector. And we know that we inserted the symbols in order, so we know that our digits are going to be in order there. The digit 1 will be the 0th entry in that symbol set. And we're going to need those for the... actually, perhaps we could just give the symbol set ID to the non-repeat regions. I think I prefer that. Okay, let's keep going. So for row in 1 to self.size, for column in 1 to self.size, let RC equal builder dot new symbol. No, new cell. Cell info new. This is one of the things I said. I said cell info was going to need a new. So for cell info. Yeah, so we're going to go impulse cell info pub fn new, which takes a name as an impl into string, and it's going to take a row, and it's going to take a col, and that's going to return a self, and it's going to be self where name is name.into, and row and col. Nothing particularly magical there. Cell info new, format row, column, col, row and col. So that's given us the cell index for this. Rows.push vec boop. No, mute. Rowids is vec boop. Oh, I don't like this. No. It's going to be a vector of empty vectors of self.size. And that's going to be a vector of empty vectors of self.size. Which means that here we can do the insertions in the right way, which is going to be rows, row.push rc. And cols, col push rc. And cells push rc. And that shouldn't be a comma, that should be a semicolon. Row is used to index rows. Yes, I know. Col is used to index columns. I know. But it's not what we're after. Yeah, that's correct. Because that means that every 9th row gets 9 columns, every 9th column gets 9 rows, and that gets all 81. What are you suggesting? You're going to replace it with 4 each? Yuck. I don't like that, but whatever. I mean, I used it before upstairs, so do it. I think it's a bit ugly, but I'd rather Clippy shut up for now. To have created our rows and our columns, we need to create our boxes. And boxes are a bit weird. Because we need to work out how many boxes across and how many rows per box. So how do we do this? Let's just have a quick think. So I don't think size should be less than 4. So I'm going to go assert size greater than or equal to 4 and size less than or equal to 9 for now. I think that's fair. Manual range inclusive contains, fine. And so we're only dealing with 4, 5, 6, 7, 8, 9. 4, 5, 6, 7, 8, 9. And within that, we know that 4 is 2 by 2. 5 has no regions. It's just Latin square. So isn't really Sudoku. 5 not Sudoku. 6 is 2 across by 3 high. 7 is not Sudoku. 8 is 4 across by 2 high. And 9 is 3 across by 3 high. So 5 and 7 are not Sudoku. So it's actually, it's not even that. It's 4, 6, 8, 9 contains. Yeah, that's reasonable. So let's just do this. And so what we can say is if it's even, then the number of cells across is always half the size. So it's always, so I don't know why I said 6 was 2 by 3. 6 is 2 cells across, 2 rows high. Yeah, so if it's even, it's always go halfway, do 2 rows. And if it's odd, it's 9, and so it's 3 by 3. So let's try and do this. I mean, first of all, let's actually insert the row and column regions. So this is going to be for row in rows. So I have a vector of cell indexes. Builder.add region. And in fact, that's going to be for n comma row in rows dot into iter dot enumerate. And we're going to add region new. I mean, guess what? We're going to have to do this, aren't we? Format row n. In fact, that's now n plus 1, comma, row. Or do we think we create a region and then we insert the rows one by one and then we... what do I want this blasted thing to look like? Let's come across here and let's find struct region. Import region. So we have 2 cells, so let's have parv new, which takes a name, which is an import of into string, I can't type, and some cells, which is an import into iterator item equals cell index. And it's going to make a self. And all we do is we go self name dot into cells dot into iter dot collect. That's probably good enough. That's therefore going to work. So that adds the rows. And let's add the columns as well. Probably should call that column. Okay, so we've actually inserted the rows and the columns, but we've not managed to record the region IDs that we've got out. And that's going to be important for the constraint that we're going to construct. So add region does return region IDs. So guess what? We're transforming this for loop. It's going to be let rows equals rows dot into iter dot enumerate dot map given n comma row close the map, collect as a vector. That smells better, and therefore let's repeat that for the columns. And it's not row, it's column. Okay. Oof. Boxes come next. So boxes is an empty vector. And I think for this, we're just going to work out the set of cells for each box and go from there. We have cells themselves, which are a 0 indexed pile of things. So we can do that. Okay, so for box in 1, 2 self dot size. We can't call it box, but we could call it box R. Okay, let me pull that up to teach us. So box 1 starts at row 1, column 1, which is cell 0. Box 2 starts at, okay, so let box W equals if self dot size mod 1 is 0, so it's even, self dot size divided by 1, else 3, because it's sod it. If self dot size is 9, so it's going to be 3, else it's going to be self dot size shifted right 1. So that's the width of the box, and box height is if self dot size is 9, 3, else 2. Okay, so let's see. The cells that we need come from where we are. So the row start is going to be n boxes wide as well. That n box W is if self dot size is 9. Actually, we can use box H for that because there are 3 across. Otherwise, there are 2 across. So the starting cell for the box is at box R so the row is, let's think, box R divided by box H. So boxes 1, 2 and 3 should give us a 0, so it's going to be box R minus 1 over box H plus 1. So start row is there, and starting column is that lot what's it going to be? It's starting column is box R mod box H. No, mod box W. No. It's box R mod box H minus 1 times box W plus 1. Is that fair? Print box R starts at row S row column, S column, panic, or to do. We don't need that for now. Right. All I want to do basically is make sure I've got my box positions right. So in main, so we had that. So we're going to go let mute builder equals puzzle builder new default, sorry. And then we're going to go Sudoku grid new 6, sorry, dot apply to builder. And that is then just going to panic because to do. Haha! The length is 6, but the index is 6, of course. Let me just get rid of that. So where did we panic? We panicked at line 31. What have I cocked up? Ah, row -1 and column at -1. Box 1 starts at row 1, column 1. That's correct. And then panicked attempted to subtract with overflow at line 57. So we can't do that. Why can't we do that? Because the mod could return 0. Yes. Right, so think again for scol. So what we know about the starting column is that it's 1, then it's 1 plus box W, then it's 1 plus box W plus box W. Ooh, I know what I can do instead. I can go let mute s row equal 1, let mute s col equal 1. And then at the end of this, we can go s col plus equals box W. If s col is greater than self.size, s col is 1, s row add box H. So row 1, column 1. Yes, row 1, column 4. Yes, row 3, column 1, row 3, column 4, row 5, column 1, row 5, column 4. Those boxes all start at the same position. And let's just confirm that again, but with a 9-cell Sudoku grid instead. 1, 1, 1, 4, 1, 7. 4, 1, 4, 7, 7, 1, 4, 7. Perfect. Right, I'm going to go back to a 6x6 because that's the type of thing that we're constructing. Put that comment there, bring that back. Right. So, 4. Box row in 1 to box height for box col in 1 to box width. Cell index is box row -1. No. Okay, so cell row is and let's go from 0 to box height and from 0 to box width. So cell row is S row plus B row. Cell column is S col plus B col. Cell number is therefore cell row -1 multiplied by self.size plus cell column -1. So the cell index is now available to us. So we're going to go let mute box cells. We're going to go box cells push cells cell index cell number, sorry. And then here we're going to go boxes push builder add region new format box box number, and the cells are going to be box cells, and that means that boxes is now a set of region IDs as well. So we've created all of our boxes. Woof. And what are we missing? Boxer. Yeah. Cool. Okay. And the final thing that we need to add to the entire grid is the constraints for those boxes for the digits. So we're going to create a new constraint. So let's do that. Mod non-repeat or mod regions. Create that, and we're going to go pub use regions non-repeat region. And in here we're going to have pub struct non-repeat region, which is going to have a region, which is a region ID, and it's going to have symbols, which is a symbol set ID. Non-repeat region pub fn new. So very briefly, this is just creating the non-repeat region, and we're going to need to import constraint for non-repeat region, and it's prep board that we're going to implement here rather than anything else. So we're going to need the solve state for this because we're going to be inserting the is it a constraint or is it a rule for non-repeat regions? Does prep board get to insert inferences? Because prep board is normally for setting up the board itself. I think non-repeat region is going to be a rule instead, and we're going to have add inferences. Rule non-repeat. I mean, if we think about killer is a rule, and killer has a non-repeat region constraint and a sum region constraint. I'm going to say non-repeat region is actually a rule. So let's pull those and let's go to rules and let's have pub mod regions. Paste that in, which is going to be not very good, but you know, we can get there eventually. Constraints is going to go, well, that doesn't have that. There's no point in that. There's no point in that file for now. We'll come back because there may be region type constraints later. but realistically these are region rules. And we're going to import rule. We should... So the constraint trait came from Kaji directly. Kaji rules. Should the rule trait come from there as well? Yes. I'm disgusting, but we'll get there eventually. Pub create mod rules. Paste that in. Pub use rules star. And that just doesn't have puzzle builder, which we can pull in. Okay. So now we can come back to... oh my goodness me. Back to here, we don't need that. Regions. So Sudoku, sorry. Rule comes from Kaji. Regions. Import rule for non-repeat region. Apply. So we're now applying a non-repeat region rule to the builder, which is going to imply that we need to get the symbols for the symbol set that we're non-repeating, and then we're going to create all of the relevant inferences for all of the cells within the region that we're meant to be non-repeating within. Okay, so let symbols equals builder dot symbols for self dot symbols, and I'll collect those into a vector. Now we're going to iterate the region cells. So let's do let cells equals builder dot. Guess what? We're going to have to define that first. I'm shocked. Are you? But before we do, let's just stick to do there. And let's come back to here. And we're going to create and apply rules for all of our non-repeat regions. So I'm going to go for region in rows into iter, chain cols into iter, chain boxes into iter. So for each one of those regions, we want to go non-repeat region, new region, and digits apply to the builder. So that completes the Sudoku constraint construction. Sorry, the Sudoku rule construction. So let's complete the non-repeat region rule construction. Leave that to do in for a moment because we need to come back to our puzzle, but let's just fix up this, which is the take rule from there to shut it up. There we go. Okay. So puzzle, like it has add region and it has symbols, is going to need cells for a region, or region cells or something. What did we call it? All cells, symbol set, cell info, solve. Did we ever have a cells in region, which takes a region ID? So we had fn region, which returns the region object, and then that had the cells. So let's do that as well, because it's only fair. And I'm going to go let region equal builder.region self.region to cells. So now we have all of the cells, we have all of the symbols within all of the cells, and we just want to add the negative inferences. let's remind ourselves how that's done within puzzle at the moment. So that's for each region. Well, we've already got that. We collect the cells for the region. We've got that. Then we say cell 0, digit in digits, cell 1, add the inference. Okay, so we need to find add inference, and that, for now I'm going to copy it, but later hopefully we can only have it existing here. I'm not sure. And we don't have implications on Puzzle Builder, so I said we might have to copy that one across eventually. So copy and paste. And I'm just going to move cell regions to there and row cols to there so that it's all in the same ordering. And what are we missing? We are missing implications. And that's unused because we need to do that and pass it over. Okay. So we're going to go for cell 0 in region.iter. Or in borrow region, why not? No, it's in 0 to region.len. Then we're going to go digit. It's going to be for digit in, or for symbol in symbols. And in fact, here we'll go symbols.iter.copied for cell 1 in cell 0 plus 1. So that's actually going to be to region len -1. Cell 1 to region.len. Builder add inference. Cell 0 has symbol. Means cell 1 lacks symbol. And then the only thing there is it's not actually that, it's region. Cell 0 and region, cell 1. And let's just double check that. Cell 0 has star digit, cell 1 lacks star digit. Yep, okay. So that adds all of the non-repeat regions in properly. So now we can get rid of the new Sudoku function entirely. And that's going to make main very sad for a moment. So we've done that, and we're going to go puzzle is builder.build. That then means that we didn't need that import. And we're going to still for now add what we're calling these constraints, but in practice, we're going to end up renaming those later. So the big question is, does this work? And the answer is yes. Oof, goodness me. And that shape looks good. So what I'm going to do very temporarily is go git stash and then cargo run. And we're going to compare those. So 354 ending 635, 354 ending 635. That's probably good enough. Git stash pot. Okay. Ooh, that was a big rework. But what that's left us with is, in theory, we could start mucking about with all sorts of things. We're going to make given digits probably a rule, because I don't think it's fair to call it a constraint. Maybe it is. I mean, it's a thing that preps the board at startup, so I would accept it being a constraint, but I would say that the given digits rule would insert the given digits constraint eventually. But that's fine. So let's just make this committed, and we'll go, so git add dot git commit. So this is add a Sudoku grid rule and make construction of the grid. We added a rule for Sudoku grids, including non-repeat regions, and we have taught it to build grids of 4, 6, 8, or 9 cells. In width, the non-repeat region will be useful for killer cages later. Forgot to tell it to sign it off, so I'll do that now. Okay. We're doing okay. So I think naked single and hidden single are not constraints. They are techniques. So let's now create the concept of techniques instead of constraints, and then these techniques realistically are pure Sudoku techniques, and so what we should do is we should have them automatically added to the puzzle builder by the Sudoku grid rule. Or, you know, we could have a standard Sudoku constraints, standard Sudoku techniques that we add them in later. So let's do that. Let's go for... we've got constraints, we've got rules, we've got symbols we want. And the reason I'm making these modules is just in case we want to add stuff in later. Create that, and then pub use techniques star. So, techniques are logical operations performed on a board at runtime to try and make progress. And the difference here I'm thinking about is I'm thinking that constraints are triggered when any cell that they're interested in changes, and that might cause them to further restrict the board. So these are mechanical restrictions, and techniques are things that look at the board and try to make a logical deduction. And I think it's quite possible that, you know, some things might be able to be both constraints and techniques, but I think they're ultimately different things that we're going to want different traits for. So I'm going to put pub trait technique. And now where I'm going to be cheeky is I'm going to say that prep board is part of constraints. There's going to be a different second method that's necessary for constraints. And this execute logical step is actually a technique thing. And I'm going to paste that in, and we're going to end up with, right, solve step, logical step. And it's not possible for a technique to not implement a logical step, just like it's going to be not possible for a constraint to not implement prep board. Yeah. Do constraints get to be registered not only with their constraint, but with what digits they care about? We'll worry about that when we need to implement a constraint that cares about particular cells. So puzzle at this point here is going to be a bit grumpy because logical step doesn't work on constraints. So puzzle is going to need not just constraints, but it's going to need techniques, which will be a vec of boxed in technique. So will puzzle builder. Puzzle builder is going to need an add technique. Which takes a T, which is a technique. Tick static. Technique T, and that's going to be self.techniques.push box new technique. Okay, and I'm going to steal that. So that doesn't need to exist on puzzle because puzzle is not going to be able to add techniques. Technique doesn't implement debug. Yep, debug. Okay, back to here. We're now back down here. So a logical step doesn't go through constraints, it goes through techniques. And technique.logical step, no method logical step found for that. Trait's going to be accessed if the trait is implemented and in scope. Well, why aren't you implementing? Why aren't you loading that in? So logical step. Oh, what am I missing? I thought I'd imported that. The field techniques is already defined. Yes, it is. Because that's still constraints. What have I fluffed up here? That. I don't think things worked quite right when I hit F2 because I think it renamed the field as well. Yeah, I think it did. I need to undo whatever it is that I did. Ah, I remember what I did. Okay. Like that. There we go. Woof. That was rough. So in constraints, singles aren't constraints, they're techniques. So let's create so let's create techniques.rs and let's go mod singles and let's mcdir kaji rules source techniques and let's git move kaji rules source constraints singles to kaji rules source techniques, and let's come into constraints and get rid of those because they're not constraints. And let's come into here and change that to technique. And we're going to import technique. Oof, technique. I mean, eventually we're going to want these, so hidden single and naked single, to be given which symbol set they actually care about, because we don't want the we don't want them to necessarily apply to all the symbol sets. So let's not worry too much about that for a moment. Let's go instead to main. You're not allowed to add those. I'm going to move that down to here, because that really should be builder. Add constraint. Puzzle doesn't get to be mutable at this point. And Sudoku grid is going to be what adds the singles the singles techniques. So it's created the regions, and now it's going to go builder, add technique, naked techniques, singles, techniques.rs, pub use singles, naked single, pub use singles, hidden single, naked single, and then hidden single. So again, we should still be good. Running 354635, good. But now we're forcing the Sudoku thing to add these constraints, because realistically they belong to Sudoku. They're techniques, not constraints. Get my brain right. And here we're adding the given digits constraint, and I'm okay calling that a constraint. I don't mind too much. Although in reality, we probably need to work out exactly how that's going to work. Remind myself. Does it find... Yeah, it uses symbol set digits, which actually we should be using from here where we create the digits. So let's just pop that constant in, which we're going to import, just because that makes sense. Okay. Yes. Sudoku grid is done. So we go, give me a puzzle builder. Apply a 6x6 Sudoku grid to it. And then apply these given digits to it. And then solve it. Excellent. That shape, I think, is good. So let's just have a look at what we've got here. We moved our singles into techniques. We have our constraints, so add everything. And this time we'll remember, and we're going to go, okay, so techniques, create the concept of a technique, migrate singles into the new technique, trait, add plumbing, make Sudoku grid, add the singles. Okay, before we go any further, I want to make sure that the singles that we've added only apply to the digits symbol set. So I'm just going to close all of those for a moment, and I'm going to come back to the singles techniques, and I'm going to say that is going to have a set, which is a symbol set ID. And we're going to import naked single pub fn new, which takes a set and produces a self, and it's going to go self set. So we've just ensured that that information is present. I'm going to do that as well for hidden single, because I can type well. This is going to be hidden single. So that's ensured that we have the information. Let's ensure we use the information. So instead of iterating across all of the sets, we're just going to use self.set. And the same should be here. Instead of iterating across all of the sets, let's just use self.set. And then here, where we construct them, new over digits, new over digits, once more. And this time singles construct over the digit symbol set. Oopsie. Okay. So again, we've not added any new core functionality yet, but we have extended our work just that little step further. I think it's time to try to bring us up to a 9x9 where we might be able to add some more classic solving techniques. So this is going to mean rebuilding our given digit array. That's okay. So let's try and find ourselves a 9x9. So easy 9x9 Sudoku. Ooh, my goodness me. How about we go? I mean, this is a lot of givens. I don't really like that. Let's go with easy 9x9 Sudoku minimum givens. Is this actually going to give us an easy grid or not? No, because I mean, it's not going to be great either way. I don't want very easy necessarily. I mean, let's hope that this needs more than just the basics, but let's actually give this a go. So step one, we're going to want a 9x9 puzzle. And step two, we're going to have some new digits. I apologize now for how long this is going to take me, but you know, this is life. So I tell you what, let's write a builder for given digits from a pattern. Yeah. So let's write from pattern. And our pattern is going to assume that it's always one character per symbol. And, you know, that it's 1 through 9 or 0 through 9 or something like that. What I'm going to do as well is I'm just going to pop this onto my other monitor where you're not going to see it, just so I can refer to it. So our pattern is 4 something 9 something something 6 something something 5 something 8 2 7 5 something 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 3 1 4 3 9 6 something 9 4 8 something 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 2 1 something 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 6 something something 5 something 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 3 2 something 1 something 7 9 3 something 5 something something 7 4 2 8 1 2 something 8 something 4 something 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 7 something 5 9 something 6 something something. So I mean, it's hideous, but there we go. Let's write that from pattern function. No, not extract into variable. I want to add this method. Pile of poo. Pub fn from pattern. To do. Of course, for this to work, we're going to have to know the size of the grid. So we're also going to have to pass 9 in. Or, I know what I'm going to do. From pattern, boop. 1 2 3 1 2 3 1 2 3 boop boop 1 2 3 1 2 3 1 2 3 boop 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 boop. Ooh. Stick a doodad on the end there. And That's going to say it's a mismatch, but that's okay because it's one of those. Because that gives us rows and columns, and that's good enough for me. So let mute digits equals vec, and then we're going to go for row in. Actually, no, it's going to be row number row in pattern enumerate. Yeah, whatever. For col number, comma, digit ch in row.chars.enumerate. Match digit char 0 to 9 becomes digits.push row number +1, col number +1, digit char as u8 minus b0. And anything else goes to nothing. And then self digits. And the final thing that we need to do is stick all of those in parens so that we've ended up pushing a tuple. And it was expecting blah blah u size found blah blah u8. I really don't like this, but never mind. It's expecting a vector of u size, u size, u size. What are we giving it? We appear to be using match for a destructuring pattern. This is true. I didn't realize we could do it that. I mean, that's hideous, but great. Wow. Okay. So if we cargo run, are we actually going to solve this puzzle? We did. And what's worse, it was all naked singles, not even a hidden single. Well, that's disappointing. But we know it worked, so. I'm gonna go sure update to a 9x9 add pattern load. Right, so clearly that puzzle wasn't a great one to do. Is there going to be a puzzle that I can find that's slightly less easy? Daily Sudoku. Still says kindergarten. How about elementary school? That seems more plausible, doesn't it? How elementary are we feeling? Well, let's find out. It's going to be 2 something, 3 something, something, 8 something, something, 7. 5 something, 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 4 something, 8 something. This all feels a bit weird. 1 5 something 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 1 something. Something 6 something. That's looking more like it. Okay. Something 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 5 something 3 something something 4 1 something 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 2 9 something something 7 something 7 something 9 8 2 1 7 6 something 3 something something 1 something something 2 4 5 and 5 9 7 2. So this one is labelled as elementary rather than kindergarten on that thing. It's still all naked singles. Ugh. Okay. High school. This is getting a bit less. 7 1 something something 8 something 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 something. 1 2 3 4 5 6 1 2 4 1 3 1 1 2 3 1 2 1 9 1 2 1 6 7 1 2 2 3 1 5 1 1 2 3 5 in the middle cell. How middling. 1 2 3 1 2 5 6 8 Ooh, haha! At least that one had some hidden singles, but we've still not needed a new technique. Oopsie. Kaji. Example of 9x9 with hidden singles. Let's try and push a bit harder. Let's go to a college grade puzzle. Sorry, this is probably one of the more boring bits, but we need to find a puzzle that needs a technique we've not implemented yet, without like jumping immediately to a super hard puzzle that I might not be able to necessarily work out how to implement the technique for. 5 9 1 2 3 1 2 3 2 3 9 1 2 1 6 4 6 1 2 1 2 2 1 2 3 1 2 3 5 Please tell me it can't solve this. Haha! Excellent! Right! We actually have something where we need to implement a new technique. Let's see, how much longer was I intending to stream today? How much longer was I intending to stream today? I was intending to stream until... Well, we've got at least an hour and a half, if not a bit more. So, what technique do we think we're missing here? I'm not sure. What I'm going to do is we're going to put this puzzle very, very quickly into Sudoku Maker, and then we're going to have a look. So, bring up Sudoku Maker. Actually, I'm going to just do this in a private tab so we don't end up getting confused by things. We're in the given digits mode. Let me just very quickly transfer this puzzle across. So there's a 4 there, and a 5 and a 9 in that box. There's a 9 there. There's a 2 and a 6 and a 4. 2 there, a 6 and a 7, a 5, 3 and a 6. So this was the puzzle that I just picked up as college level. The puzzle has a solution and it's unique. I'm going to use Sudoku Maker's logical solver here just to see what kinds of things it does so that we can work out what technique we're missing and we can implement that. So, nakeds and hiddens, that all makes sense. And in fact, if we pop across to here, we can go, well, we had some naked singles, row 2, column 8, row 5, column 9, row 2, column 8, row 5, column 9. We then had some hidden singles in boxes and columns. our hidden singles were in rows and columns, but I mean, ultimately, whether you find it in the row or the column or the box, it doesn't really matter. Ultimately, we found 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22 digits. And then there was a naked pair, and then everything else was singles again. So it's pairs that we need to think about. How do we do that? Well, if we restart and we step until we think we've hit where the naked pair is going to happen, then we can see what it is. Is that right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 18, 19, 20, 21, 22, 23 is where it does a naked pair operation. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So this is the state at which it decides there's no more naked or hidden singles, and it's looking for what to do next. And what it finds is a hidden pair, or a naked pair, but importantly, it finds a pointing pair. And what it's doing is it's noticing that those two cells in this particular box are the only cells that can contain 3. Is it 3 and 4? No, it's going, there's this naked pair here, 4 and 6, which is eliminating 4 from those cells. That's the operation that it's doing. So it's a naked pair. So what we're basically interested in here is saying if there is a region in which there is a pair of cells which contain only a given pair of digits, then we can eliminate those 2 digits from the rest of the cells, assuming there's anything to be done about that. So this is kind of like naked single, but it's a tuple. And can we make this generic, or should we just do it for pairs to begin with? Let's just do it for pairs to begin with, but we can think about doing it generically later. So we are writing a new technique, and it's a tuples technique. So mod tuples, and pub use tuples, and for now we're just going to do naked pair, because that's the only thing we need to solve this particular puzzle. So pub struct naked pair. Naked pair is a technique, again, that's operating on symbols. So we're going to have a set, which is going to be a symbol set ID. We're going to need to import naked pair, pub fn naked pair. Sorry, new, which takes a set. Gives back a self set, nothing complicated there. Import technique for naked pair. And bring in these. Okay, so our technique is going to be for every region in the solve state, we are going to look for, well, we're going to take all the cells, all the digits in the cell. We're going to look for cells that contain only 2 digits, and where that choice of digits is equal between cells, so that we can go, these 2 cells have these 2 digits, therefore it's a naked pair. We'll worry about doing the more complicated stuff another time. Okay, let's just put to do in there for a moment so that we're good. Naked pair doesn't import debug. Now it does. And naked pair is a Sudoku technique. So let's add it here. Add technique naked pair over the digits. So let's actually make that happen. And what we can do is, first of all, we can confirm that we end up with our, oh, we couldn't do a naked pair exactly after the hidden single 7 in column 7, which was exactly the state that Sudoku Maker got to as well. Oof. Okay. Right, where are we next? So what we're looking for is cells which contain only 2 digits. Or, I'll tell you what we're going to do. We're going to go choices, which is going to be a hash map. We're just going to say it's a hash map for now, and we'll work out what's going in it in a moment. So we're going to go for cell in state dot region brackets. Oh no, we need to go, okay, for region in state dot regions. For cell in region dot, state dot region dot to cells. Let choice equal state dot choices for cell self dot set. So we've now got a symbol choice, which is going to tell us how many options there are in that cell. If it's solved, we'll just continue. So if choice dot solved, continue. Otherwise, in fact, let's just go if not choice dot solved, choices dot entry choice dot or default dot push cell. And let's be clear here, this is a hash map from symbol choice to vector of cell index. Is this allowed? Let's find out. Import. It is. And that will need to be mute. So the method entry exists for this, but its trait bounds are not satisfied. Symbol choice does not have EQ or hash. Okay, that's fair. So we now need to make it so that it's possible to say, given this choice, let's do the thing. So here we go. We're going to come to symbols. We're going to find symbol choice. So raw symbol choice is also going to have to implement partial EQ and EQ and hash, which it can. And then in puzzle, symbol choice is going to have to derive, we can go debug, partial EQ and EQ and hash, which means that symbol set ID will need partial EQ and EQ and hash. I mean, adding all of these is not exactly onerous. Right. I'm going to rename naked pair to be naked tuple. And our rule basically at this point is going to be if a given choice has n choices available and n cells, then we're going to eliminate all of those choices from all of the other cells in that group. Whew. I mean, this is complicated, but you know, we'll get there. Okay. For choice, comma, cells in choices. If choice dot options dot count equals cells dot len. So the cells in cells, the n cells in cells, all share the same n options. So what we want to do is eliminate all of those from all of the other cells in the region. So I'm going to go, let's go let region cells equals state.region region to cells. That is going to be region cells copied. This is not going to be a vec, it's going to be a hash set. See, I dislike the fact that 2 cells is giving me back a vector, but I really don't want to bugger about, so that's going to be into it. Collect hash set. I just want to do everything with sets here. So that's going to be insert. Others is going to be region cells difference intersection disjoint. The cells representative are the references that are in self but not in other. Yep. So others is going to be region cells difference cells, and it's just going to be, you know, for cell in elims is going to be format naked tuple on at. Oh dear, describing this is going to be painful. Let's not describe it for now, let's just do the work. So for each cell in there, we need to eliminate all the choices that we are currently holding. So we're going to go for option in choice.options. So state dot. Is there an eliminate? But there isn't yet, but we're going to add one. Cell option. Right, and we're going to write that method. So let's come up to puzzle. Let's find import solve. There. So set symbol is like we're solving it. Eliminate. What do you get? Yes, it is a symbol ID. Self.puzzle. Eliminate. Board, cell, and choice. Yeah, I mean, realistically, that should be symbol. And that should be symbol. And now we need to add this method. So set symbol is also going to have an eliminate. Board. Cell. Symbol. So we're not going to say it has to be that. We're just going to say choice.eliminate symbol number and propagate changes board cell. Oh, actually, let's be cheeky and let's go let choice copy equals star choice. If choice does not equal choice copy, propagate the changes. Self.eliminate, pods, it's fn, eliminate. Choice is a raw symbol choice. Can't compare borrow mute symbols raw symbol choice with symbols raw symbol choice. Blah blah blah. So we can go for star choice does not equal choice copy. That's fine. And now we need to generate this method. And so this is how we eliminate this particular value from here. So this is just going to be self dot 0 and equals not one shifted left symbol number. Oh, that is unset. We already have that. So I don't need to add a method here. I'm going to unset that. What I need to know is whether or not that made a change. So I can make... So let's have a look. So our technique here is just going to do that elimination. But if that doesn't make a change, then we didn't do any work. And if it does make a change, then we want to say, okay, we made a change. We're going to let other techniques kick in again. So let's first of all describe the tuple that we found. Tuple. Actually, so it's going to be let mute ret equal format. Tuple, which is going to be cells.len. So we've decided that it happens. So we're going to name the tuple, and the tuple is then going to be ret dot push. I don't know. I can write this in, so I can say let cells equal cells dot iter copied map given the index state dot cell info for the cell dot format into borrow, no, stupid, right, borrow mute ret that, and it's probably not let cells equal, it's probably just cells.iter.copy.for each that comma space do I need that? No. I need to bring std.io right in, not std format display. It's always more difficult to make the pretty things than it is to write the damned code. Right format exists for mutable reference borrow mute string, but its trait bounds are not satisfied. Is it not? It's not IO right? Is it format? right. Oh my goodness me, I'm just not going to do it this way at all. For cell in. Ret.push. I mean, I'm doing this hideously inefficiently, so let's not do it until we need it. And we can always report the tuple differently. So let's go let mute changed equals false. Changed or equals see, I don't like it returning a bool, so let's have an enum. Doobie-doobie-doo, raw simple choice, blah blah blah. So here we're going to have whether or not an action actually altered the board. Pub enum effect unchanged changed. Impl effect changed. So that derives debug clone. Copy because it's trivial. And there's our changed method. And now we have to go and write our eliminate. So fn eliminate effect changed else effect unchanged, which means that eliminate returns an effect. And then we have to find our other eliminate method, which is here, and that returns an effect. And we get rid of that semicolon. And now we know whether or not we've changed any cell in this region, in which case we're going to return a logical step acted, found a tuple. That'll do for now. Otherwise, we all get to the end and we go logical step, no action. Found a tuple in region. Region is state.region. Region dot name. Probably formatted like that. Okay, so we're not getting anywhere particularly. We found our tuple, but we're stuck. So what are we trying to do with our tuple in row 2? It's that. So we're trying to eliminate 4 and 6 from anywhere else in the grid. So let's, rather than found a tuple, let's panic instead, because that's always fun. And then let's see what we're going to do to tell us what we were up to. Okay, so we can go println tuple in region. Println trying to eliminate option from cell. And that's going to complain that those don't get to be what's did, but we can make debug just to see what's going on. So it's symbols 3 and 5, which are 4 and 6 from each of the cells. And let's just print changed out. Ooh, it's ended up eliminating itself. It's ended up eliminating itself from itself. So we can't do that. If I do that, it's going to say, oh, no, we didn't manage it. Oh, my return should only have happened if changed. Oh, for God's sake. I'm such an idiot. Get rid of that. Move that down. Get rid of that. If changed, that. There we go. So, found a tuple in column 8. Then it found a tuple in box 2. What tuple did it find in column 8? So it found that 5, 9. But that didn't do anything not in column 8. It found that 5, 7, which did eliminate 5 from there. Fair enough. I mean, it's not a particularly helpful thing for it to find, but it can find that. And then it found that 4, 6, which eliminated 4 from there, gave us that naked single 3. Yep. So we can get a better textual description of the tuple and its actions now. So let's do that. So we have to create the description of the tuple right at the start, because we have to say which cells the tuple was found in, and then what it eliminated, therefore, from which other cells. So we're going to go let action equal format. So step 1, we need to describe the tuple. Yeah. So action is format blah tuple found in region, where the blah is cells.len. And for now, if we just say that we acted with action, it's to tuple found in. So the next thing we want to do is we want to add to that action the values in question. So let's go mute, and then we're going to go for cell in cells. Action push str format cell comma space, and we're going to go let cell equals state dot cell info for cell, and we need to push borrow of that. And that's going to have to be cells copied. So now action pop, action pop, action push str close paren. So we've got, like, say, two tuple brackets thing comma thing close brackets. Eliminates space. So rather than that, we're going to go let did equal that, and we're going to go changed or equals did. if did action push str format symbol from cell. And symbol is going to be state symbol option. Cell is state. Cell info cell. Comma space again. Action pop. Action pop. So 2 tuple found in column 8, row 1 column 8, row 3 column 8. Eliminates 5 from row 7 column 8. 2 tuple found in box 2, row 2 column 6, row 2 column 4. Eliminates 4 from row 3 column 4, 4 from row 3 column 6. Haha! We have pointing tuples, and in theory that will work for triples as well. Right, git add. Let's have a look. So we've upgraded to something that needs naked tuples, and then we've implemented our naked tuples. And to be frank, more work was necessary to implement the description, but that's fine. Git commit. Okay, so technique, add naked tuple, add a naked tuple technique and a puzzle which needs it. Right, I mean, in theory, we can go on to an even harder puzzle at this point. So let's go back to here and let's see if we can get a harder puzzle. Let's go to graduate puzzles. I don't know if we're actually going to be able to even solve one of these, but let's find out. So 3 and 6 and 8, 2, 8, 4, 7, 3, 1. There's a 1 and a 3 there. A 9, a 7 and a 1 there. 5 and 8 and a 7 there. 9 and 8, 1 and 5, 4, 5, 7. So we're just going to find out what's necessary here and see which technique it is that we're going to need to implement. Hidden pair. Hidden pair. Pointing pair in box 5 removes 3 from there. I mean, that's also potentially more complex. Naked pair, hidden pair, finned X-wing. Okay, we're not going to be implementing that one right now because I'm not going to even begin to think about implementing finned X-wing. What can we get which perhaps doesn't need an X-wing but could work for what's it pairs? I mean, if we run that again and we find out when did it need the finned X-wing. Finned X-wing on 9s in row 2 and 9 removed a 9 from those locations. Oy. Naked single at row 5 column 1. One of the difficulties with these things is, you know, working out when. There you go. Right, so this is the thing. Finned X-wing in 9s, removed 9 from these 2 cells. 9's in rows 2 and 9. So if we look at rows 2 and 9, we can see that the 9 is there or there. And in row 9, it's there or there. So this is why it's a finned X-Wing rather than a normal X-Wing. The normal X-Wing would be that 9 was there, and the only elimination would be from that. But the fin means that if that's a 9, that's a 9. That can't be 9 by either. And if that's a 9, then that's not the 9. That can't be 9. No matter which of those. So that's why you eliminate 9 from both of those. But, coding that's going to be a pig. I don't like coding that. So let's see which of the 9s happens. It happens there. So if I just put that 9 in as a given, do we need anything other than nakeds? Naked pair, naked pair. So we do need to implement hidden pair and pointing pair possibly if we end up there. Let's run to the pointing pair. So the thing pointing pair is naked triple. Oh yes, okay. So to solve this puzzle, we're going to need a bunch more techniques. So let's give this puzzle to our thing. Right. Ooh. If I push that, I did. I like this. Let's teach it the puzzle. So the puzzle is 3, 6, 8, 2, something. Something, 7 something something. Four something 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 5 9 something something. So that was the puzzle as given by Sudoku9x9.com. And then what we're going to do is we're also going to go... So what we're going to do, we're just going to get that used so we can go... And we're going to go row to column 5 is 9. Because that was the fix, I think. Yeah, row 2, column 5 is 9. So in theory, remove this constraint to need finned X-Wing. I don't know that we're ever going to implement that before we just decide to go to a slightly different set of constraints, but if we now cargo run, we're going to get stuck. So we found a 2 tuple, 2 tuple, 2 tuple, and then we failed to solve. And the reason that we found those tuples, did some eliminations, but then failed to solve is if we remember from this path, yes, we had a naked pair and a naked pair, but then we had a hidden pair. Did we do the naked triple? No, those were all 2 tuples. So this naked pair is what we need to... Sorry, this hidden pair is what we need to evaluate. So that was after the second naked pair. First naked pair in column 3. Removed 2 and 4 from row 3, column 3. Naked pair in column 3, row 4, column 3. Right, so that's that 2, 4. Removed it from those 3 things and also those. So we actually see that as 2 different naked pair operations because we see it in the column and then we see it in the box. That's fair enough. I'm not going to worry about, I found a pair, now I need to futz about. I'm just going to accept that I did that. So we get stuck after finding those tuples. So we found that first naked pair. The second naked pair happens. And then the next operation is going to be the hidden pair or hidden triple, I can't remember which. Hidden pair in column 8 removed all of the candidates other than 1 and 7 from those. So hiddens are where you have two cells which are the only two cells which could contain those two digits, and so you eliminate everything else from those. So now you have a naked pair, and that's okay. That naked pair may never do anything else, but you have it. And then the next thing was this naked triple, which I think was one of our two tuple things, maybe. And then we had a pointing pair in box 5, row 5, column 4, and row 5, column 6, removed 3. So pointing pair we're going to have to do after we've done hidden pair. And that's okay. And all pointing pair is basically saying is, in this region, every cell which could contain a 3 is in this region, and therefore in this region, these are the only cells that can contain a 3. Two techniques, hidden pairs and pointing pairs. So we're going to do hidden tuples, and then we're going to do pointing tuples. And if we do hidden tuples and pointing tuples, then after the pointing pair, it's all singles. Okay. Let's see where we can get to. Give me one moment to sort myself out with another drink, and I will be right back. Okay, typical me. I spilled the drink that I was preparing all over the place. Right, so the technique that we're going to implement is hidden tuples. So these were our naked tuples. So we're going to do the same for hidden tuples. So let's yoink all of that. Hidden tuple. Right. And let's make sure that our Sudoku rule adds the hidden tuples constraint. Sorry, technique. And that's not going to work until we bring it in. And then here we can pull it in. And that should be digits. So we're now constructing the technique into our grid. So what we need to do now is work out how we're actually going to implement hidden tuple. So let's come back here and let's clear this out and run again until we hit that one. So our hidden tuple is that these two cells are the only two cells in this box that can contain 1 and 7. So how do we find that? Well, essentially what we can do is we can say that ignoring the solved cells, because they're not going to be relevant to us, we're going to say for each option, which cells can contain the option. And then what we're going to do is we're going to say for all of the sizes 2 through 8, presumably, because there's no, or rather 2 through size -1 of the grid, which we can do by symbol count. If we can find n symbols that have that number of cells, then we're good. Blah. I'm not explaining that well. Let's build the data structure. So what we want to do is we want to go for region in state regions. And if we get that far, then it's no action. Okay, so in this region, we want to find for each symbol in our symbol set, which cells in the region could be that symbol. And I mean, we can do it for the solved symbols as well, because it won't make any difference because they'll all be one cell. It can be that solved symbol. So let's, what am I going to be saying next? I'm going to be saying that, oh, hey Tristan. We're going to say that, okay, let's grab all the symbols actually, for our symbol set. So symbols is state symbols for our set. We may as well just collect them into a vector for now. So in this question here, what we're asking is which symbols map to which cells. So let's go, let's say that sim map is hash map from symbol ID to a hash set of cell index. Right. For cell in state dot region dot to cells, let choice well, we can just go better than that. We can go for option in state dot options cell. No, state. Oh, for goodness sake. I can remember my own APIs, honestly. State.choices cell for set dot options. Goodness me. State choices cell for set options. Right. So this cell can be any of these symbols. So sim map, entry, option, or default insert cell. And then sim map will need to be mute. So we've now constructed that particular data structure. So for now, let's dump it out and panic. And it's going to complain something rotten that symbol ID is not found in this scope. Import that. And we're good. So when we run this, we're going to get as far as we can and then panic with the data structure that we're trying to think about at the moment. And I mean, this is not joyous because obviously we're looking at the first region, not the region that we care about, but we can see in this data structure that symbol ID 3 is found in cells 1 and 3. Symbol ID 2 is found in 0, 1, and 5, and so on. And like symbol ID 0, which is a 1, is found in cell index 6. So we're actually looking at row 1, if we think about it from a region perspective. Cell 6 is row 1, column 7, just by simple mathematics. So row 1, column 7, 1, 2, 3, 4, 5, 6, 7 is a 1, which is symbol ID 0. So we can see that we're definitely dealing with row 1, and we're thinking about this thing. Now, quite obviously, we're not going to find what we're looking for in row 1. So I'm actually going to insert something that just continues until it hits the region, which is box 9. So what's that going to be? It's going to be... Let's go for... state, region. Yep, so it's saying row 1. So let's go. Astra is format state, region. If Astra does not equal box 9, continue. And I'm just being cheeky about this at the moment because we're interested in seeing the box 9 data structure, which is this data structure. And specifically, we're interested in knowing about 1s and 7s. So we're interested in symbol IDs 6 and 0. So if we look at symbol ID 0, which we can see here, that's cells 70 and 61. And if I can spot symbol ID 6, which is here, that's cells 61 and 70. So those happen to have the same sets. So basically our question is, for pairs, triples, quads, and so on, can we find a pair? Can we find n symbols that have an exactly overlapping set of cells? Okay, so we've made our symbol map. So our next action is to go, for tuple n in 2 to did I get all my symbols? I did. Symbols.len -1. Tuple n. Let's just check that. Yeah, so we're going to look for pairs, triples, quads, 5 tuples, 6 tuples, 7 tuples. We should look to 8 tuples as well, really. I mean, it's fairly irrelevant, but we should. And what we are hoping for is we're hoping for n symbols where the cell count matches that. So what we're now going to look for is we're going to say, okay, how many cells we'll get? Jeepers. Doing this generically right now is going to be a pain. So let's only do it for pairs, and we'll worry about doing it for triples and so on later. So what we're interested in is we're going to go, for cell 0. Tell you what, let's capture the cells because at the moment we haven't captured the cells. Extract into variable. We've got the cells, so we're going to go for cell 0 in 0 to cells.len -1. For cell 1 in cell 0 + 1 to cells.len. So if the set of cells, sorry, for the set of, oh no, we're trying to do it for symbols, not cells. Stupid me. for symbol 0 in 0 2 symbols dot len minus 1 for symbol 1 in 1 2 symbols len. Sorry, not 1, but sim 0 plus 1 to symbols len. So for each pair of symbols, if the cells that those symbols can be in is a pair, we found our hidden pair. Yes, okay. So if sim map dot, so square brackets, symbols symbol 0, let's go, cells 0 is equal to that, and cells 1 is sim map symbols symbol 1. So it's if cells 0.len is 2 and cells 1.len is 2 and cells 0 cell 0 equals cells 1. Hidden pair. To do. Otherwise, we go around again. And now what we can do is we can say that we're going to get rid of that, and we'll say found a hidden pair in state regions region. What's wrong with that? State region. Stupid. Found a hidden pair in row 1. Did we? No, it was naked. Should we store the choices for the cells? I mean, it's not a hidden pair because the cells wouldn't have anything eliminated from them. So we found a pair, but is it a hidden pair? So we know it's hidden if either of those cells has more symbols in it than 2. Yeah, okay, so if state dot choices for cell if cells 0 dot we know that they're equal, so dot any dot iter dot any given the cell copied state dot choices for the cell and our set dot options dot count greater than 2. And it's found a pair in column 8. So that was that hidden pair. So it found it in column 8 rather than in box 9. That's fair enough. That doesn't really bother us. We can find it anywhere. You know, any region can give us it. We just found it in the column rather than the box. Fair enough. And we can collapse the nested blocks. So it's just... Right. So we've definitely found a hidden pair. So now we need to act on that hidden pair. And the act that we're going to perform is to eliminate everything but that pair. So how does Sudoku Maker describe that when we execute it? It says the hidden pair in column 8 removed all candidates other than from there. Whew. Okay, so let mute acted is format hidden pair in blah eliminated. I know, because we're gonna put the cells next. Hidden pair in blah colon blah and blah eliminated all but blah and blah. I don't really need to repeat the cells in my view. So the region is state.region region. The two cells in question we need to extract from the sets. Okay. Cells equals cells 0 dot iter dot copied dot collect as a vector. I mean, this is all just in order to be fancier about these things, but it will enable me to go state.cellinfo for cells 0, state.cellinfo for cells 1, and eliminated all but symbol symbols symbol 0 symbol symbols symbol 1. Okay, crikey O'Reilly, we've generated the description string. We know that we're going to act because everything but is being eliminated. So all we need to do now is perform those eliminations. So we can go for cell in cells, for option in state dot choices cell self dot set dot options if option does not equal symbol 0 and option does not equal symbol 1, state eliminate cell option, return logical step acted. That does not need to be mutable. Right. I mean, that's done the hidden pair elimination, and then it gets to fail to solve. Well, the next step is a naked triple. In row 5, column 1, column 2, column 3, so that's that 5, 6, 9. Removed 5, 6, and 9 from there. So why couldn't we get a naked 3 tuple? Is it because our naked tuple thing is wrong? The The n cells in all cells share the same n options. So the problem is, of course, that when we get to the triple, it's actually not the same n options. It's that the union of those n cells have those options. How am I going to do that? You know, if all of those were 5, 6, 9, then my current algorithm would work. But because it's not all of them are 5, 6, 9, it can't. I mean, effectively, again, we're looking for 3 cells where the union of the digits in those 3 cells does what we need. So this is for choice, comma, cells in choices. Yeah. That's just not going to work for triples. It's only going to work for pairs or for triples which are very, very clearly not eliminated at all yet. So we're going to have to come up with a more efficient way of doing that, and I don't have the brain for it now. So the techniques that we're at the moment, we can find hidden pairs, which, you know, we'd like to extend to hidden tuples in the future, but we can't for now. So we're just going to put, you know, to do hidden tuple can only see pairs with this horrid code. We should improve it. And here we're going to say to do, ideally, we need to take groups of symbol choices, union them together, and check the cell count. Otherwise, a triple of AB, ABC, BC doesn't work. And I think at this point, I'm going to have to say that this particular puzzle we're not going to get solved today. I have, I think, run out of the brain necessary to get any further. So unless any of you that are watching have any idea how to, then I think we're probably going to call that there. And next time that we come in, we're going to try to, first of all, improve the naked tuples. And then we're going to try to improve the hidden tuples. And remember that this puzzle, then, if I run it through again, so we've done the hidden pair, we solved that. We couldn't get the naked triple, and therefore the pointing pair that we were meant to see, because that's coming from row 5, we didn't get to do that either. But we'll find that hopefully next time once we've solved the triples. Okay, I may as well commit this. So tuples, add initial hidden tuple, hidden pair support. We noted that our naked tuples don't work beyond full tuples, i.e. AB, ABC, BC doesn't work as a triple. So we'll need to fix that next time. Right, that's all pushed up. I'm sorry that we didn't actually get to make this particular puzzle work, but we will get there. And I mean, in theory, after we've got there, we could potentially even worry about removing that extra given digit and trying to implement finned X-wings, but I'm not going to do that in what's left for 30 minutes. It's just not going to happen. So just as a recap of everything that we've done today, we implemented Puzzle Builder, we implemented the Sudoku grid rule, so that rather than hard coding a 6x6 Sudoku, we now have a 9x9 that does what we need. That particular rule, having constructed all of the regions, adds our new techniques that we've split out from constraints. So we now have constraints and techniques. The moment given digit is our only constraint, but in theory we could add new constraint types like killer cages and so on in the future. That all of the mechanisms that we need are now present, except for noticing when a cell has changed and applying constraints to that, which we'll do the moment we have a constraint that we need that for. And then we played around, we switched up to 9x9s. We verified that we could do hidden singles. We verified the naked pairs. Unfortunately, naked triples aren't working. And then we started to add hidden pairs at least. I mean, I'd like to get that fully up to hidden tuples next time. So thank you very much for watching, and I will see you next time.